Welcome to Chapter 5 in CHEM24. Today I'll be talking about gases. So the objective of this chapter is first to describe some of the physical properties of the gases, and then we'll derive the ideal gas law, and with that we can calculate changes in the conditions of the gas. We will talk a little bit about how when we have a mixture of gases, their partial pressures can be used to describe their properties. And then we'll do some stoichiometry calculations as well that involve gases, either as reactants or products. Then just very briefly, I'll also talk about the kinetic theory of gases. The kinetic theory of gases is a little bit complicated and it's a little bit theoretical. Well, it's a theory, so it's very theoretical, but it's a useful way to understand where the gas laws can come from, what's the physics behind it, and not just qualitatively, but quantitatively, how the observed behavior of the gases can be obtained. Now, we'll talk a little bit about, coming from that, about the distribution of speeds of the gas molecules, and then also how it relates to the temperature and the molar mass of the gases, and that's important as well. And then we'll talk a little bit about gases when they don't behave ideally, and we'll kind of come to a new equation, that's the van der Waals equation, which we can use to perform calculation on gases that are not behaving ideally. And so remember that we talked about the various physical phases, and then one of them, of course, was the gases, how we, so that they expand to fill the volume of any container, right? So they don't have a definite volume or a definite shape. They have much lower densities than solids and liquids. Well, what does it mean, lower density? Lower density means that on average, the molecules, the particles in a gas are farther from each other, much farther than in a solid or a liquid. And then also the densities vary a great deal depending on the condition, right? You can take a gas, compress it half its volume, and of course the density will double. You cannot do that with a solid or a liquid. And then also that they mix with one another readily and thoroughly, which means that a mixture of gases for us will behave the same way as individual gases, one by one. And then also, if you change the temperature, then the volume changes dramatically. What does it mean dramatically? Well, if you heat up a solid, it will change its volume, right? That we know. But it will change only very little. However, if you change the volume of the temperature of a gas, then let's say if we're at room temperature and then change it to 100 degrees, a whole 30% will be the increase in the volume, and we'll see how we can calculate all that. And one of the most important quantities description of a gas will be its pressure. Okay, what does the pressure come from? Well, the pressure is a result of the various molecular collision between the gas molecules and the container walls. So the way you can picture a gas is that these little particles just fly around. When they meet another gas particle, they bounce back from each other, and when they hit the wall, they bounce back from the wall. And when they do that, they impart some force on the wall, and this is the reason why we have pressure. Each of these collisions imparts a small amount of a force, but of course we have lots and lots of particles, and so it adds up to a considerable pressure. That pressure is actually so high that right now, as I'm speaking, at 1 atmosphere pressure, that pressure is equivalent to 10 meters of water, and 10 meters is a lot, right? If you go to the UOP pool, I think that's about 4.5 meters in its deepest part, and if you swim all the way down, and you see your ears are popping because it's such a huge pressure, and that's not even half of the pressure experienced now. But of course that pressure is both inside and outside, but it's a huge pressure as those little collisions add up to considerable force. And so the macroscopic property of the pressure is coming from all the microscopic forces that the molecular collisions give you. So for example, when you look at this balloon here, you can see that these little particles, actually they're way too close to each other, but nevertheless, those particles will hit the wall and bounce back from the wall, and that's where the pressure is coming from. But how do we measure pressure? So as you know, in physics, the pressure is force over the area, right? And so right away, the SI unit would have to be the SI unit of force over the SI unit of area. And so in SI, right, the SI unit of force is Newton. Right, the area is measured in square meters, right, because the length is measured in meters. So Newton over square meters would give you the SI unit, and that we call Pascal. Okay, now a much older measurement is based on the realization that you can have a column of a liquid, preferably dense liquid, in this case mercury. So the force that is coming from this much mercury here can be in equilibrium with the force from the atmosphere. And if the two forces are equal, then this line of mercury is in equilibrium, it's not going anywhere. Now, for that, what you need is that you have to have a vacuum here, right? Otherwise, if you would have also the same outside pressure, then there would be zero difference in the mercury levels. But if there is no gas pressure there's vacuum, then only the height of the mercury will counteract the force of the atmosphere here, right? So the mercury counteracts the force of the atmosphere, and so the height is proportional to the pressure. And so one unit could be how many millimeters of mercury we have, and that we call torr. That's coming from Torricelli's name. And then roughly, they realize that it's less than 1,000 torrs for an atmosphere, and it's actually defined to be exactly 760 torrs. Now, you have to memorize this number because we'll do a bunch of conversions between atmospheres and torrs. So 760 torrs is 1 atmosphere. Now, this is also defined based on the SI system. So 100,325 pascals, or newtons over square meter, is exactly 1 atmosphere, right? So this will also give you a connection between, torr and atmosphere, right? Because 760 torrs is 101,325 pascals. Now, you can already see that that's one of the reasons why we don't usually measure with pascals, and like we're SI Nazis, and that is because the pascal is just a very, very inconveniently small unit when it gets to pressures we usually talk about, right? A whole 100,000 pascals is 1 atmosphere. And so oftentimes we use atmospheres, or we use torrs. Or there's another unit which is quite convenient, at least more convenient, 101,325, and that we call a bar, right? So 1 bar is defined to be exactly 10 to the 5th pascals. Okay, so it's just like an atmosphere, but it's a nice round atmosphere in terms of SI units. So it's exactly 100,000 pascals is 1 bar, and that's actually the unit that most people use in the international community. In the US, atmospheres are more common, but you should know that bar is actually there. And in fact, if you buy certain vacuum equipment, certain vacuum gauges, for example, then the exact same unit in the US will be sold with a scale in torrs, okay? And if you buy the same in Europe, for example, the same equipment, same everything, it will show you the pressure in millibars, right? Why millibars? Well, millibar is approximately, well, not exactly. 1 millibar is exactly 100 pascals, right? And so that's close to a torr, right? Because torr is 760th of an atmosphere, and then 1 millibar is 1,000 of a bar, which is close to an atmosphere. So the torr and the millibar are close to each other, not exactly the same, and there's like 30% difference between them, but they're both very good to measure low pressures, such in vacuum equipment. Now, how can we measure the pressure. So if we have a closed container of a gas, how can we measure its pressure the simplest way? Okay, well, I'm talking historically because now you would connect it to a barometron or something and just read the pressure. But let's see how historically it was done. So what if you have a gas and that has a lower pressure than the atmosphere? Then what you need is that pressure, right, which is measured here, the pressure of a gas, plus the pressure that is coming from this line of mercury. That together will give you the atmospheric pressure, right? So outside here, let's say when we have 1 atmosphere or whatever the atmospheric pressure is that day, and so the gas pressure here would be this atmospheric pressure minus the height of the mercury, right? Because the inside pressure is smaller than atmospheric. What if it's larger than atmospheric? If it's larger than the outside atmospheric pressure, then the atmospheric pressure plus the difference in the mercury would give you the pressure of the gas here, and so there's a plus sign. But if you know the outside pressure, and you can do that with, for example, this previous one, right? So this would measure the outside pressure. You can just measure the length of the mercury column, and then if you put the two together, then you would get the pressure of a gas inside, and that is going to be extremely important when we come to some of the gas laws that all involve, or some of them involve, pressure. So what we'll do now is we'll derive historically the ideal gas law in 3 steps. What we want to do is describe how the gases change when the conditions are altered. And by conditions I mean temperature, pressure, number of moles, and how the volume changes upon these changes. And then we'll be using 3 empirically determined gas laws. So we'll have 3 gas laws. One is Charles' law, which is the relationship between temperature and volume. Then Boyle's law is between pressure and volume, and Avogadro's law determines the relationship between how many particles, or how many moles of particles you have in a gas, and how it relates to the volume. And so Charles' law, since it's between the temperature and the volume, we will say that the pressure and the number of moles are constant. Okay. For Boyle's law, the temperature and the number of moles are constant, and then between the relationship between number of moles and the volume will be upon the pressure and the temperature being constant. Okay, and when we have these 3 equations, we can put it all together and then describe a relationship that is the ideal gas law. So 3 laws together lead to the ideal gas law, which will tell us how the pressure, the temperature, the volume, and the number of moles of the gas are interlinked. So the first law that I'll be talking about is called Charles' law. And Jacques Charles, he was the one who studied the relationship between volume and temperature, right? So how the volume and the temperature of a gas are interrelated. So how do you plot the volume against the temperature? And so these plots here, they're of different gases. So this one is for helium, for methane, water, and so on. Now you can see that some of these lines are extrapolations. So for example, the water line only runs to 100 degrees, right? Because there it condenses into liquid water. Then hydrogen goes almost all the way down, right? So that's a good one. Helium, same way, right? So this is a long line down there. And so there are 2 things that you can see. One is that they're all lines, right? So this means that the volume of a gas is directly proportional to the temperature, right? Or there's a linear relationship. And furthermore, if you happen to measure it in Celsius as the temperature, then you see that all the lines somehow they extrapolate down to minus 273.15 Celsius. And so there seems to be a minimum temperature, an absolute zero temperature, and that absolute zero temperature corresponds to zero volume for all the gases, right? And then all the lines actually end up in that. So if you have the temperature measured in a unit that starts it's zero at that point, and let's call it Kelvin, then the volume is directly proportional to the temperature. So if the temperature increases 2-fold, then the volume will increase 2-fold as well. And so if the origin is expressed on the Kelvin temperature scale, where the 0 Kelvin is the minus 273.15 Celsius, then all those lines will be strictly proportional. So a percent change in the temperature will be the exact same percent change in the volume, right? And so this is the important relationship. If you have a constant pressure and then you don't change the number of moles of gas, which just means that you're still talking about the same amount of gas, then the volume and the temperature, if it's an absolute temperature, are directly proportional to each other. And that is at minus 273.15 Celsius. Now, for some reason, the book and other books as well, they list minus 273. It's not that. It's 273.15, and I expect you to use 273.15, partly because, let's say, CHEM25, that book uses the proper value. So I see no reason why we want to pretend that you're, not advanced enough to use, those decimals. So minus 273.15 is the number, and you're, of course, expected to memorize it. And so let's see how we can use this in an actual problem. And so we have a balloon, right? And that balloon is filled with helium. The volume is 2.2 liters at 298 kelvins. And so what we do is we put that in liquid nitrogen, and so the temperature of the gas will rapidly decrease. And then when the balloon has cooled to the temperature of liquid nitrogen, so the new temperature is 77 kelvins, what will be the volume of the balloon? So how can we do that? Well, if you go back to the previous one, we'll see that the volume is proportional to the temperature. Or I can also say that the volume over the temperature, or the temperature over the volume, is constant. Okay. I can do it either way. I think it's more customary to use temperature over the volume, but it doesn't matter. So let's say that we have initial temperature over initial volume, and that is equal to the new temperature over the new volume. And all we have to do now is put in the numbers, right? So the initial temperature was 298 Kelvin, the initial volume is 2.2 liters, and then the new temperature is 77 kelvins, and now I'm looking for the new volume. So how can I do that? Well, it's not, rocket science. It's 2.2, right, times 77 divided by 298, right? And so what I get is the new volume is 0.57 liters, if I can read it well. And then how many sig figs should I have here? Well, this is 2 sig figs, right? This guy here is 3 sig figs, and then this number here is 2 sig figs as well, right? And since everything was expressed in kelvins, we didn't have to do any conversion to between Celsius and Kelvin at all, so we can just use it directly, and the answer is 0.57 liters. Now, what about the next one? How about the relationship between the pressure and the volume? And so for that, one kind of an experiment that you can devise is you have this manometer, right? And you have a gas in one of the lines, and then the other one is connected to atmospheres. And so the inside pressure here is going to be the atmospheric pressure plus the height of the mercury. And so one way to increase the pressure rate there is to add more mercury, right? If I add more mercury, right, added mercury, then there will be an added pressure on the gas, which will compress it. I can read that pressure, right, again from the height and then the outside atmospheric pressure. So what I can do is I can measure the height of the gas, which is then, because I know the inside diameter, I would know the volume of a gas. So I will have these pressure volume pairs, right? I keep adding mercury, I measure what the new pressure is, what's the new volume, and then I come up with these numbers, and then I plot it on a diagram where the x-axis is the volume and the y-axis is the pressure. So I have these lines, and what I will find is that the pressure times the volume is always a constant number, right? If I increase the pressure by a factor of 2, then the new volume will be half the original volume. Okay, and so if I rearrange it, then this will be that the volume is directly proportional to 1 over the pressure, right? And so this is Boyle's law, and now I have a relationship between the pressure and the volume, but of course the temperature and the moles of the gas will be constant. So how can I use this to solve a problem? Well, it's actually very similar to the previous one, and it doesn't say, but the temperature is constant here, right? And I have a cylinder which is a fixed, which has a certain pressure, 154 atmosphere. The volume is 49 liters, and what I do is I expand the gas from this cylinder into some giant balloon and let it expand until the pressure falls to 1 atmosphere. So how can you picture it? Well, this is the cylinder, right? And then the cylinder is now connected to a valve through a balloon, right? And then the balloon just goes goes very large, right? And so the total volume of this plus that is what we're looking for when the pressure dropped down to 1 atmosphere, which means that the whole system has 1 atmosphere. Now, of course, this means that the balloon does not exert any additional pressure, right? It probably would, right, because it's made of some stretchy material. But let's just say that the pressure is just coming from the gas itself. And so from the previous slide, remember that the pressure times the volume is constant. So the pressure times volume before equals pressure times volume after. And all I have to do is put in the numbers. So the original pressure was 154 atmospheres. The original volume of the cylinder was 49 liters. And the new pressure is 1.00 atmospheres, and I'm looking for what is the new volume. So all I have to do now, this is even easier because it's going to involve, dividing by 1, right? So I'm not going to do that. So what I have is the second volume, and then how many sig figs do I have? I have 3 sig figs here, 3 sig figs there, and 3 sig figs there. So I have to give it to 3 significant figures, which will be 7,550 liters as the new volume, right? And if I were to put it in here, then the PV, the P times V would be equal in both cases. Okay, so now we have a law that describes how the pressure and the volume of a gas are interrelated. And then the third law, and then we will use these 3 laws together to construct the ideal gas law. It's about how many moles of the gas are we talking about and what would be the volume under identical conditions. And so what it says is that the volume and the number of moles of the gas are directly proportional, right? So the volume is directly proportional to the number of moles. What does it mean? Well, if I have the same pressure, right? Same pressure, and then the temperature is also constant. That's of course very important. And if I have some way of adding additional moles of gas, one such way could be, dropping a little bit of dry ice if we're talking about carbon dioxide, let's say. And so whatever, but we have a way of adding more moles of gas. If I have 1 mole or 2 moles or 3 moles, then the volume under identical pressures will double or triple accordingly, right? And so the volume again is proportional to the number of moles of the gas. And so if we put these 3 together, let me see what we're talking about, right? So we know that the volume is proportional to the temperature, the volume is proportional to the number of moles, and the volume is inversely proportional to the pressure. And so what I can do is I can put all these in, right? I will put on the right hand side the ones that it's proportional to, that would be the temperature and the number of moles, and then I can put the 1 over P on the right, but I multiply over, so the P goes over here. And so what I have is P times V is proportional to the number of moles times the temperature. And so that proportional, I can just use a constant, any constant that I can come up with, and then set the value of the constant. So a measurement confirms it, for example, and I call that constant the R. It's the universal gas constant. Now, bad news. This is another number that you have to memorize. And so in this ideal gas law, which connects the pressure, the volume, the number of moles, and the temperature of a gas, the proportionality constant is called R, and we'll learn it both in SI units and in imperial or North American whatever units. And so the SI unit would be 8.314, and let's talk a little bit about the what is the unit for it. Okay, so the R is 8.314 joule over mole Kelvin. So how do we get joule when we don't see any energy related stuff here? So let's start out with putting in the pressure, and then pressure was, of course, Newton over square meter, right? Remember, because it's force over area. Then I multiply it with volume, which is cubic meter, right? And then on the right hand side I have moles, that's the unit for mole, right? And I have Kelvin, right? And then I have here that R that I'm looking for. And so the unit of the R is going to be whatever is on the left divided by mole Kelvin. And then interestingly, you can see that there's a bit of a cancellation here. So the square meter will cancel out, you know, square meter on the right, which will turn this into just meter. So I have Newton meter divided by mole Kelvin. And we all know that Newton times meter is actually the measure for work, and then work is a type of energy, and so that is simply joule. So joule over mole Kelvin is the unit for the R. Now what about these customary silly little units? So if I use liter and if I use atmosphere to measure the volume and the pressure of the gas, then of course the PV is still, you know, PV, and that divided by mole Kelvin would be the unit, and in that unit is 0.08206. Now which one of these you have to memorize? Well, in principle only one, because the difference between them, the connection between them, would be 101.325, because, you know, the liter is 10 to the negative 3 cubic meters, and the atmosphere is 101.325 pascals. So when you multiply the two together, then the difference, right? So 1 liter atmosphere is 101.325 joules, right? And so in principle, if you learn one, then you can calculate the other one. But nevertheless, there are two numbers that you have to memorize, either the 101.325 and one of the R's, or just both R's. Why do you have to use the SI in the first place when most of our calculations are going to be in liters and atmospheres, unfortunately? Well, the reason is that in this chapter, when we're only talking about gases, then the ideal gas law will be useful in terms of liter atmospheres. But later, when let's go to the energy chapter or the entropy, then you see a whole new use for the R, and there the natural unit is going to be in SI, and so therefore the 8.314 is also one that you have to learn. But either way, the important part is that we now have a relationship between all four parameters of a gas, and let me write it out again. So P times V equals nRT, and then this is the single most important relationship in this entire chapter. Okay, now units. There are some other temperature units, but remember that they have to be on an absolute scale, right? That it has to be a measure of absolute temperature. Celsius is not an absolute temperature. God forbid Fahrenheit is even less an absolute temperature. Well, it's also not the absolute temperature, not even less. So in some fields, what you can do is like shifting the Celsius scale to make it into absolute temperature, and then it turns into Kelvins, right? And so keeping the graduation the same, but now shifting it by 273.15 Celsius, that gives you the Kelvin. And along the same way, you can take the the Fahrenheit scale and then shift it so that it's 0 will become the absolute 0, and then we call it the I'll call it Rankine. I'm not sure where it's coming from, I pronounced it correctly or not. And then 0 Rankine unit is also 0 Kelvin, right, because it's absolute, right, absolute temperature scale. But 1 Rankine unit is 1.8 Kelvin. So what does it say? Well, it's 9/5, so it's the same graduation as the Fahrenheit, right? So if you take the Fahrenheit, shift it so that it's 0 becomes absolute 0, then you get the Rankine scale. And then it says that some engineering fields use that. Please don't. Okay, there's absolutely no good reason for that. The Kelvin is perfectly fine. It's both an engineering and scientific unit, so let's just stick to that. But if you ever hear this Rankine, when you stop laughing, then just know that it's 1.8 times the graduation of the Kelvin scale. Now, of course, the unit for moles is always the mole, and then various pressure and volume units. As I said, the two important ones for us will be the SI unit, the 8.314, and then for some of our calculations, we'll be using this liter atmosphere thingy, 0.08206 liter atmosphere over mole Kelvin. All right, so that's enough about the, introducing the ideal gas law. And let's see how it works in action. So we have a gas of ethane here, C2H6. And then the volume is 575 cubic centimeters, and then we have a pressure of 752 torrs and 72 Celsius. And so this just designed to be an ugly one in terms of all the units. So let's start with the volume, right? So the volume is 575 cubic centimeters, and let's say we want to solve this problem in liters. And so I will have to convert it. The cubic centimeter is the same exact business as the milliliter, so it's 1,000 cubic centimeters for 1 liter, and so we have 0.575 liters for the gas. What about the pressure? The pressure is 752 torrs. Right, but I want to put it in atmospheres. So 1 atmosphere is 760 torrs. Torr cancels out, and I do need a calculator for that. So 725 divided by 760, and I get something like 0.954 atmospheres, right? And this is what I will put in my calculation. What else is there? Then the temperature is 72 Celsius, and I add 273.15, and so well, it's kind of lame, but I put it in a calculator just because I'm lazy, and that will give me 345.15 kelvins. Now let's talk a little bit about sig figs, because I know you love them. So how many sig figs are we talking about? Well, this here is 3 sig figs, right? No question about that. This is 3 sig figs as well, and that both of them were converted with a multiplication or division. But here, this guy was converted by an addition subtraction, and I know that a bunch of us had problem in the first midterm with converting between Kelvin and Celsius and keeping the right number of sig figs. But let's just see, we're adding 273.15 to this. So where is the last significant figure? And the question is where and not how many. The last significant figure is here. And therefore, when I add it up, this is the last significant figure. So how many significant figs do I have? I have 3 sig figs. So even though I gave you the temperature as 72 Celsius, that 72 Celsius for the absolute temperature is not 2 sig figs, it's actually 3 significant figures. Alrighty, so what I'm looking for is now the mass of the ethane, and the mass of the ethane, of course, will then come from the moles. So the PV equals nRT can be rearranged to N equals PV over RT. So let's do that. So the number of moles is going to be the pressure, which is 0.954 atmospheres. But don't forget, don't round it, okay? We need all the digits, so I will put it in the calculator as 725 divided by 760, okay? And then I multiply it with the volume of 575 liters, and then I divide it with the R, which is 0.08206 8206 liter atmosphere over mole Kelvin, and then multiply it with the temperature of 345.15 kelvins. And if I do all that, okay, so I take the pressure, multiply it with 575 divided by 8206. Let me just check, it's 8206, right? That's the one I usually don't like to memorize, and 345.15 Kelvin. And what I get is 0.019 blah 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 4 moles, okay, of C2H6. But I'm looking for the mass, and so how do I get the mass from this? Well, I convert it into grams by 1 mole of C2H6, and let's add it up. So the molar mass is 12.011 plus 1.0794. Is it 00794? Or yeah, oh, I was 94, okay, times 2. So if I calculate right, I get 26.0. Let's do another digit, 4 grams of C2H6. Now it looks really ugly, but nevertheless, if I multiply this conversion factor with the moles, then what I get is 0.504 grams of C2H6. And let's just do a little check here, okay? We're not there yet, quite yet at least, but let me just tell you that roughly at room temperature, 1 mole, okay, at room temperature, 1 mole will occupy at atmospheric pressure roughly 25 liters. Okay, so let's see. We have instead of 25 liters, we have about half a liter, so it's 50 times less. The pressure here is roughly an atmosphere, and then the pressure is the temperature is just a little bit above room temperature. And so what I'm expecting is approximately 50th of a mole, and that would be 1/50th a mole would be roughly the 25 grams per mole here. So divided by 50, I'm expecting about half a gram, and indeed what I get is half a gram, and so the calculation is probably okay. Now I understand that you don't have a feel for this yet, but it's very, very important to build one, because after a while when you do these calculations, the first thing to check always is, does it even make sense? So what if I calculated, instead of 0.5 grams, I calculated 500 grams? Now I look at it as half a liter of gas at normal pressure and close to room temperature. That cannot be that much, and so then I check my calculation again, and probably I made a mistake of multiplying or with 1,000, or failing to divide by 1,000. Let's say if I use the liters instead of cubic centimeters, right? So just it's good to build a sort of a number sense for these kind of things. Now this was all kind of simple so far, because we're talking about one gas. We put one gas in a container, whether it's a balloon with the with a variable volume, or we have a cylinder that has a fixed volume. But how about we use a mixture of gases? And so the interesting thing is, and then of course, why is it relevant? Because air is a mixture of gases, right? And we've seen that we only had one ideal gas law, right? So the PV equals nRT. I didn't say that, okay, and by the way, this is valid for helium, or this is valid for CO2. No, it's an ideal universal gas law, and the universal gas constant is the same constant for all the gases, which kind of means that the gas law doesn't depend on the identity of a gas. Okay, and then the pressure just simply comes from how many total moles of a gas you have. And then the reason for that is that gas molecules just fly around, they hit the walls, they exert pressure that way, but it doesn't matter what kind of a gas that is, right? You always get the same pressure for the same amount of a gas at the same temperature, and so on. And so one visualization would be, if I have a certain volume, right? This is my volume here, and if I have 4 moles of this gas, then this is going to be the pressure, or equivalent to the pressure it exerts. If instead of that 4 I now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these, then accordingly I have 10 over 4, so I have now 5 halves that much pressure. And then it doesn't matter what the kind of gas it is. And so if I add these two up together, and now I have 14 moles, then the pressure will be just simply the pressure of the two. So the partial pressure, the pressure that is coming from the blue gas molecules, I'll call it P1. The partial pressure of the red ones, okay, would be P2, and then the total pressure is simply the pressure of these two, and that's the pressure of the gas mixture in there. Okay, and then what you can also see is that the partial pressures are just directly related to how many moles of the gas you have in there over the total moles. And then the total pressure adds up from the partial pressure of the gases. And this is just ugly. I think there should be a sum in here. And so the total pressure, apparently my iPad cannot display this figure. And so we have a law, Dalton's law of partial pressures, which says that the total pressure of a mixture of gases is simply the sum of the partial pressures of its component gases, right? So you take the individual partial pressures. So what is a partial pressure? Well, can you measure the partial pressure? Well, not really, right? Because what you're measuring is just the total pressure. But what you can do is devise an experiment in which, in the same exact size container, so here, you just put in that gas, you measure the pressure, and then the same size container, you put in a different gas, measure its pressure. And when you put the two together, same amounts, then you should get the sum of those pressures, right? And so they just add up like that. And then furthermore, right, since each individual pressure, each individual P1, right, for, let's say Pi for any component of gas, times the total volume will be equal to the number of moles of that gas times RT. The V and the T are the same, right? Because it's the same temperature and we're talking about the same gas. And so each partial pressure will be proportional to the number of moles, right? We've seen this is one of actually two of the constituent Avogadro's to put together with well, it's actually all three, whatever. So it's the ideal, coming from the ideal gas law simply. And so what we can say is that the individual partial pressures come from how many moles of that component you have over the total moles. And then how can we express this? Well, we can use the so-called mole fraction. The mole fraction is the moles of a particular component over the total moles, and the total moles is of course the sum of the individual moles, right? So if you take this mole fraction and then you use it to multiply, so this is the Ni over N, multiply with the total pressure, then you get the individual pressures, which also means that if you take these equations, right, and then you add them up, then you get the ideal gas law for the total mixture of the gases. Okay, so what do you have to remember here is that the individual partial pressures add up to the total pressure, and the individual partial pressures are proportional to the mole fraction of that component in the total gas. And so let's see how this works in real life. And then just one more thing is that sometimes I will give this not as mole fraction ending up. Let's say if you see and then you add up, they add up to 1, right? Because the sum of the mole fractions will be 1. I can give you the moles instead, and then you would have to divide each mole with the sum of the moles to get the mole fraction. But furthermore, especially in an exam, I can give it to you in grams. So for each component, there's a certain number of grams, and then you convert it to moles, add up the moles to get the sum of the moles, and from that you get the mole fraction, right? So I can also frame the question like that. But this is, we just get started. So what will be the partial pressure of each of the gases? And so what I can do is, let's say for methane, the partial pressure of methane here is going to be the total pressure times its mole fraction, and the mole fraction for methane, right, and that would be 750 torrs times 0.865. That of course is unitless, right? And so 750 times 0.865 is going to be 649 torrs. But how many sig figs do I have? Well, this guy only has 2 sig figs. Don't forget that the 0 does not qualify in this case, so I get 650 torrs of partial pressure for the methane. And similarly, you can do it, for CO2, you can do it for ethane, you can do it for the propane there, just using their individual mole fractions and multiplying it with the total pressure, right? And then they have to add up, so you calculate for all three. They have to add up to the total pressure of 750, if of course these mole fractions do add up to the to 1. Okay, do they add up? At least, well, you have 2 odd and 2 even numbers, so at least it's not definitely out of question. And so if we got that far, how about the individual moles of the substances? How many moles would I have to put in? So I opened a new page so that we have enough room here. How many moles would each substance be needed? So we have a 15-liter total vessel. We know the temperature. We know the total pressure, right? So what was the pressure? The total pressure was 750 torrs, right? 750 torrs. And so first I can calculate using the ideal gas law just the number of total moles, so the total number of moles with PV equals nRT, and from that the N equals PV over RT. But instead of that, why don't I just and then from the N, the individual number of moles will be the mole fraction times this number of moles. So I can do that, or I can take the calculated partial pressure here and then put that partial pressure into this, and then using the P for each individual component times V equals N of that component RT, right? So what I calculate from the previous goes in here, and then I would get the individual number of moles. So if I did all the calculations on the left hand or the previous page, I would do that. But in this case, why don't I just calculate this total number of moles and use the mole fractions? So how would that go? Well, first of all, the number of moles, that's an ugly N, a number of moles is pressure. So I will do it as 750 torrs, right? And then I convert it on the fly to atmospheres, right? By dividing it with 760. Okay, so I could also calculate it separately, but this would be simpler here. And then I said it's 15.0 liters. And then what else do I have? The well, obviously the R 8206. I'm slowly learning, liter atmosphere over mole Kelvin, and then times the temperature, and the temperature is given as 30 Celsius. We'll discuss that in a moment, but that just gives me 303.15 Kelvins. But I'm not saying this is 5 sig figs. In fact, well, how many sig figs is that? Give it a few thoughts. And you should have set 2. Why 2? Because the last significant figure here is the 3, which is in the tens, and it's an addition, right? 273.15, which means I will always also have it in the tens, and that will be this significant here. So the 3 and the 0 are significant, the 3 after that is actually not. But of course, when I do the calculation, I'll use all figures, right? Don't round it yet, but just remember how many we have. And then 0.8206, and then also divided by 303.15, and what I get is 0.595 moles, and so that's the total number of moles. And so if I want, for example, the moles of the methane, I think that was the first one, what I have to do is the total number of moles times the mole fraction, which is 865. Again, that has no unit. So if I do that, 865, then I arrive to 0.5. Again, it was not asking for this, so this is, I haven't rounded it, right? So this was not rounded. But now I have to round this, and I remember that I only have 2 sig figs here. Plus I actually have 2 sig figs there as well, right? 750, the 0 is not significant, so I will have to round it. And if I round it correctly, then I have 0.51 moles. Just note that since we're rounding here, and when you're adding up the rounded number of moles for the other gases, you may not find the exact same one here. After that, I can get the CO2, I can get the other 2 components, and each will have, you know, the total number of moles times the mole fraction, that will be 0.029, and so on and so forth, and you would get the other 3 numbers. Okay, and then they all have to add up to this total number of moles. All right, so this is a very typical question and typical problem, and definitely I like putting such stuff into the midterm or final exams. And again, it can be given in mole fraction, it can be given in grams, and any such way you should be able to calculate it. Okay, let's do a bit more. Okay, and so I have a 40-liter vessel here, and the temperature is 120.0 Celsius. So now I have 4 sig figs in Celsius, which will also translate to 4 sig figs in the kelvins, because it starts with 100. And then I have this many grams of 3 components: water, SO2, and CO2. Okay, it's a little bit silly because I would actually probably react, but nevertheless, what would the partial pressure of each of the gases, and then what would be the total pressure? And so the partial pressure will just be obtained from this equation, right? So each gas component, as you remember, will obey its own ideal gas law, right? So the partial pressure times the total volume of the container it's in equals its moles times RT. And when we add this up, then the sum of the moles and then the sum of the partial pressures will result in the moles and the total pressure in one nice PV equals nRT ideal gas law. And so if I want to calculate the partial pressures, it would be then, let's say P water. Okay, that sounded silly, right? P water. So the pressure of the water vapor is going to be the number of moles of water times R times T divided by the volume of the container. And the number of moles, we don't have it, but remember that mass divided by molar mass will give you the moles. So the mass of the water divided by the molar mass of the water times RT divided by V will give us the pressure. And so let me not write down everything, but this is 15 grams, right? So the number of moles is 15 grams, and then here this is something like 18, so 9994 plus 2 times 10794, and that is 18.015 grams per mole, right? And so if I put in the temperature, which is 393.15 kelvins, right? I added 273.15, but again, the last significant figure is here, so we have 4 sig figs in that one. And then the volume is just this 40 liters here, right? 40.0 liters. Now let's just discuss sig figs a little bit. So I have 3 sig figs in this one. I have 4 sig figs in that one. 3 sig figs here. I have as many as I want there, similarly to the R. So I will have 3 sig figs in the end. And let me put the numbers in, and hopefully I won't make any mistakes. Of course, I cannot guarantee that. And then times 0.08206 times the temperature is 393.15, and then the volume was 40.0. If I got it right, I have 0.67. How many sig figs? 3, so 2. atmospheres. Now, let's discuss this a little bit, okay? So, again, I told you that at room temperature, 1 mole of a gas is approximately 25 liters, okay? But we have about 100 degrees above it, okay? And room temperature is 300 kelvins, so 100 degrees above it is 30% higher, okay? So 1/3 higher the temperature. And then the volume is approximately 1/3 higher than 25, a bit more than that. And I have a little bit less than 1 mole of a gas, right? Less than a mole of a gas, more than 1/3 higher of the volume, so that decreases twice, so I should get between approximately half an atmosphere and 1 atmosphere of pressure, and the number I got is 2/3 of an atmosphere, which is perfectly nice, and so I probably did not make any serious mistakes there. Okay, now how about the next one? So the partial pressure of the SO2 would be done exactly the same way, except that, you know, you have the 3.5 grams here, right, divided by the molar mass of the SO2, and that just roughly 64, right, something like 64 grams. RT over V is exactly the same, and that would give you now the pressure, the partial pressure of that, also in atmospheres. And then you do the same thing for CO2, right, the partial pressure of CO2, but of course I get bored easily, so I will not actually do that. And then you add up the atmosphere, so this plus that will give you the total pressure in atmospheres. Another way of doing that would be first to use this mass over molar mass to get the number of moles of water, right? And then the total moles is the number of moles of water plus the number of moles of SO2 plus the number of moles of the CO2, and you add them up, you get the number of moles, and then put that number of moles into this ideal gas law, which will give you directly the pressure. I actually encourage at home that you do well, first the individual partial pressure, so this one, that one, and that one, and then you get the total pressure, and then also do it by calculating the number of moles here for each species, ending up to the total number of moles, and then putting in the PV equals nRT, and you should get, of course, the same value, of course, within rounding errors to each other. Very nice. Now, next thing is, and that's going to be maybe the most complicated part in terms of calculations of this chapter, and that is how to do stoichiometry calculations with gases. And remember, the stoichiometry calculation, its heart is in moles. Okay, so first we just took the moles of a reactant and then calculated the moles of a product. But then how to get the moles? We typically get it from the grams and then convert grams to moles, and then from moles we convert back to grams, and then we also did some calculations involving aqueous solutes, so things that are dissolved in water or something else, but typically water. And there we use the concentration and the volume of the solution to get the moles. But again, the moles was the center part of the or the moles were the center part of the calculation. And the question is, for a gas, how can we convert to moles? And what we can do is use the ideal gas law, right? Because the number of moles of a gas is connected to the temperature, pressure, and volume. And so if we know what the temperature and the pressure are, then we have a connection between how many liters of a gas we have and then how many moles it corresponds to. So if I tell you the volume of a gas and along with pressure and temperature, then I can get the moles, which I can use in the stoichiometry calculation. And at the end of the stoichiometry calculation, the question may read like, what volume of a product do I get? And then use it similarly to get the volume from the number of moles. And so let's see such a problem, and then we'll introduce a significant simplification to it. But let's just in an arbitrary pressure and arbitrary temperature. I start out with 1.4 grams of sodium bicarbonate, and I react it with hydrochloric acid, which is in excess. So all I have to use is the moles of the sodium bicarbonate, and then the question is not the grams of the product CO2, but I want is the volume of the product here. So how can we do this problem? Well, first of all, of course, we need an equation, so let's not forget about that. The reaction is sodium bicarbonate reacting with HCl, forming sodium chloride, water, and the CO2, and the CO2 is the gas, and that's what we're looking for. That was an error, just an ugly one. Okay, so what we want is the number of moles of CO2 from the number of moles of sodium bicarbonate, and then luckily the ratio is 1:1, so that part is going to be easy. So let's start out with 1.4 grams of sodium bicarbonate, and then I want moles of sodium bicarbonate. So 1 mole of sodium bicarbonate is, and then this is where I need a periodic table, but luckily I have one in front of me. And let's see where the 9, 8, 9, 7, I probably, 8, 9, 7, 7, I probably overdid that, plus the hydrogen is 1.00794. Well, I should know that by heart. 1.0107 plus 3 times 15.9994. Okay, so that is 84.007 grams of sodium bicarbonate. Let's just check quickly in my hand. So that's 48, 60, 61, 84 indeed. Okay, so I have now the number of moles of the sodium bicarbonate, but I want is, the moles of the CO2, and I have 1 mole of CO2 for each 1 mole of sodium bicarbonate, right? The ratio is 1:1 in this reaction, and now I want it converted to volume. So how would I do that? Well, remember that the PV equals nRT, and I can rearrange it so the volume is number of moles, which I have, times RT over P. And so this looks a little bit strange, but the volume of a gas will also be simply a matter of a conversion between, the moles and the volume, and the conversion factor is RT over P. And so all I have to do is add this in. So 8206 liter atmosphere over mole Kelvin, and then I have the temperature, which is 290.15 Kelvin, right? And then I divide with the pressure, which is 722 torrs, converted, right, to atmosphere, as 1 atmosphere is 760 torrs, right? So that divided by dividing, so actually that goes on top, but I can put it in either way. And so that would give me, let's see the cancellations. So the torr cancels the torrs, then I'm dividing with atmosphere, so atmosphere there, then the Kelvin cancels out the Kelvin, the mole here cancels out the mole there, and so I'm left with liter of CO2. Isn't that wonderful and marvelous? So all I have to do is just multiply the whole thing together. So 1.4 divided by the molar mass, and then multiplied with that 0.0806, multiplied with the temperature, and then divided by 722, multiplied by 760, and that gives me 0.42 liters of CO2. Well, that looks interesting, doesn't it? But let's see if it makes sense. So again, 1 mole of a gas gives me approximately 25 liters at room temperature. Now we're a little bit lower than room temperature, a little bit lower than atmospheric pressure, so it's going to be a little bit less than that for a mole. And then the question is, how many moles do we have? Well, if I had 0.08 grams, that would be exactly 1/100th of a mole, and I have approximately twice that. And so what I'm looking for is approximately well, 1.5 times that. The pressure is a little bit lower, and so I'm looking for approximately between 0.25 and then 0.5 liters, right? For the 25 liters, 1/100th of it would be 0.25. We have approximately 50 to 60% higher than that with the 1.4 grams here, and so I'm looking for something less than half a liter. Now I just got it right. And what we have here is approximately right. So the 0.42 liters sounds approximately good. And then also remember that we have 2 sig figs here. So 2 sig figs. And then I have 3 sig figs there. And then here I have how many sig figs? 3, correct? Why 3? Because again, it's an addition, so these are the 3 sig figs I have there. How many sig figs do I have in the 760 down there, the conversion? The correct answer is infinite, right? It's defined to be exactly 760. So you would look at it as it's 2 sig figs, but no, it's infinity because it's a definition, right? That's the definition. That's a conversion factor between torrs and atmospheres. Wonderful. So we could calculate it, but it was kind of ugly and long and not terribly pleasant. And then the reason, of course, was this big conversion here from the moles to the liters. So is there something easier than that? Well, one thing that we can realize is that it had nothing about the actual gas, right? It was just, the temperature, it was the pressure, right? But it did not say that it was CO2 and nitrogen. And so the conversion between the moles and the liters is independent of the type of the gas. It depends on the pressure and it depends on the temperature. So if I say that let's use some standard temperature and standard pressure, or let's call it standard temperature and pressure, and let's call it STP. Then at STP, I can just calculate what is the volume of 1 mole of a gas, whatever gas it is, and then use that conversion. What will I call it? Well, I'll call this guy here the molar mass. Why do I call it molar mass? Because it's the mass of a mole. And so if that is so, then the volume of 1 mole I could call the molar volume. And so if I calculate the molar volume, or VM, at STP, and I use that number for any gas or any calculation later. And so that leads us to this definition of STP. Now, if you look at the Wikipedia page for STP, it's actually quite fascinating. There's so many definitions depending on which country you are, and then what profession uses that STP. And so our definition of STP, at least in this country, in this book, in this classroom, virtual or not, is that we're at 0 Celsius, okay, and then 1 atmosphere. So exactly 273.15 Kelvin in 1 atmosphere. And if I put it all together, then I can calculate the volume of 1 mole of a gas. All I have to do is put in exactly 1 moles here, put in the R, then the temperature is 0 Celsius or 273.15 Kelvins, and put exactly 1 atmosphere in there, and then I have the STP of 22.41. And that molar volume is a very nice conversion factor for stoichiometry problem between the mole and the volume of a gas. All I have to say is that since this is the volume of 1 mole, I divide it over 1 mole, and so it's 22.41 liter over mole. And I don't have to say for what, because it's true for any gas that behaves ideally. Okay. How can we use this for a problem? Okay, so instead of calculating it, the laborious way, or for any arbitrary temperature and pressure, if the pressure and temperature are STP, then we can just use this number here. So let's start with that. Now we start out, instead of grams of something and converting in the end to liters, start out with liters. So 5.50 liters of CO2. Well, this is a different reaction. So let me write up equation. So CO2 reacts with the calcium oxide. By the way, this is a very important reaction. This is why houses are coated with calcium hydroxide, calcium oxide, and then over time it reacts on CO2 of the atmosphere, and then turns into limestone, and that limestone is now water resistant, on the side of on the walls of the house. And so what this gives me is calcium carbonate, right? And then it's 1:1, so it's very, very simple. Okay, so I have the liters of CO2, but I want the moles of CO2. And I know that 1 mole of CO2, or 1 mole of any gas, is the 22.41 liters of CO2. Okay, and so I use this because I'm at STP. And now, since I have 1 mole of CO2, but I want the moles of calcium carbonate, and then it's just 1:1, so that's a simple one. And then I have to multiply with the conversion between the moles of calcium carbonate and the grams of calcium carbonate, and that is so calcium is 40.078 plus 12.011, whatever, plus 3 times for the oxygen, that's exactly 100, that's right. So it's 100.08, so let's say 1 grams. And then if I multiply everything in, what I have is 24.56. How many sig figs do I have? Well, no more than 3 here, right? So 24.6 grams of calcium carbonate. Now, let's see if this is correct or not. And I guess this is getting boring, right? So I have 5.5 liters, and I said that at room temperature we have 25, and now you know that at 0 you have 22, and so we have approximately 1/4 of a mole of carbon dioxide, and 1/4 of a mole of carbon dioxide will give you 1/4 of a mole of calcium carbonate, and then since it's 100 grams, 1/4 of it will be about 25. So we're looking for something around 25 grams, and 24.6 gram is just awesome. Okay, so again, don't forget this step. I know that that a lot of you trust your calculator better than you trust yourself, but don't, right? A calculator is just as good as your fingers were when you punch in the numbers, and it's easy to make little mistakes when punching in numbers. So what I always recommend is try to use your head, right? That's much better than any calculator, and then try to always estimate your answer just to check that that what you did actually makes sense and it's the correct number. At this point, let's review again how we arrived to that ideal gas law. So we had 3 gas laws that were all individually determined or found by prominent scientists. And when we put those 3 together, then we got one law which connects, the pressure, the volume, the number of moles, and the temperature of a gas. And then the ideal gas law's universal gas constant, the R, is the same for any gas under normal conditions. Okay, so this was found by experiments. But what is the physical basis? What's the theoretical basis to this? And that gives that leads us to this kinetic molecular theory of gases. And that kinetic molecular theory of gases tries to describe how we think the gas molecules behave, what is the physics behind it, and then tries to arrive to the same formula that we came to from experimental data. If we get the same formula or similar formula, then that can give us further insight into what's underlying that ideal gas law, but also it validates our picture of how gas behaves. So first of all, the gases are made up of very large collections of particles, okay, and they are constant random motion, right? So just fly around. They're very small, they're infinitely small, they occupy negligible volume. Of course, we know that's not true, right? We know the size of an atom, therefore we know the size of a molecule and all that. But compared to the volume that the gases have available to fly in, right, that is the size of a container, their volume is negligible. That's important. Now, these gas molecules, when I say constant random motion, they move in straight lines, except when they collide. They collide with other particles or with the container walls. Now, furthermore, the first one of these, when they collide with each other, that doesn't matter. Why do I say that? It's just because if it collides with another particle, then if it's totally elastic collision, it means that the kinetic energy of particles is conserved. And so if my particle is going in this direction and then hits another one, and now that one will fly in this direction and goes back, then the velocities are conserved, the kinetic energies are conserved, and then ultimately one of the particles, and it doesn't matter which one, will also hit the wall. And this is the important part, that when they hit the wall, depending on the velocity and their mass, they will impart a force on the wall. And we know that the pressure is force over area, and so we can get the pressure. So what we can do in this theory, we have this box, and then we look at the velocities of the particles, and then furthermore in 3 dimensions, we first dump it down to just 1 dimension. What about the x component of the velocities? What is the mass, the velocity change when it hits the wall, what force, what pressure it corresponds to, knowing the area, and then we can put it all together. Now, in this course, we're not doing it, but if you take, let's say, CHEM25, we actually derive the equation. So we start with elementary physics, the velocities and all that, and put it together. And the important thing is what we arrive to is that the average kinetic energy of a gas is proportional to the absolute temperature. And so if the average kinetic energy of a gas is simply a measure of what's the absolute temperature, then we can use these assumptions that I just mentioned and arrive to the same formula as the ideal gas law. And so this tells us that this is correct, and then indeed the temperature is just measure of the average molecular speed, but in the form of the kinetic energy. And let's just review, if you forgot your physics, that the kinetic energy is the velocity squared times the mass. And then since every particle travels with a different velocity, there are random distribution not random, there's a certain distribution of velocities, and that we're averaging. And so this is an average of these, but the average is not in terms of velocities, but velocity square, and so the root mean square average, and I'll explain that in a moment. That gives me the average kinetic energy, and that average kinetic energy, that Ke average, is proportional to the absolute temperature. And that's what temperature means, right? Back in kindergarten, when you first encountered temperature, probably before, right? The first time you touched something that was hot, and then you screamed and said, oh, this is hot. Then you realize that there's a certain thing called temperature. And then when you first looked at the thermometer and then realized that, well, it's 25 Celsius here, it's in room temperature and all that, then you could even quantify the temperature. But do you ever think, what is exactly the temperature? What is the temperature? And now we know that at least for a gas, it's a measure of the average kinetic energy, that is how fast these particles are moving. And then, of course, this also makes sense from our ideal gas law, when we realize that the pressure and then the temperature are interrelated, right, at the constant volume. And so if we have higher temperature, then the molecules will be moving faster, they collide more often, they collide with greater force, and therefore they exert a higher pressure. And that, of course, makes sense. If we heat up the gas, then the pressure goes up. And then a few more things from the model. So when you look at a particular temperature, let's say 300 kelvins, then every gas particle will travel with a different velocity. Okay, but these velocities average out to that value that we just discussed, right? And so there is a distribution. And so what this shows is that on the x-axis I have the various speeds, and then on the right axis we have the distribution. So how many we have, what is the probability of finding a particle with a certain velocity. And that leads us to this very nice looking distribution, which we call the Maxwell-Boltzmann distribution of speeds. The Maxwell-Boltzmann distribution tells us what is the probability of finding gas particles at a particular velocity. And you can see that we have particles with close to zero velocity, and we also have particles with very high velocity, and then we have a bunch of ones at average velocities. And when we increase the temperature, remember I told you that the temperature is a measure of the average kinetic energy. And so what this means, if I increase the temperature, so go from 300 kelvins to 500 kelvins, then the average kinetic energy will increase. But not just that, but also the width of the distribution increases. And you can see that even better in 1000 kelvins. So there are two effects. One effect is, as I increase the temperature, the average velocity or average kinetic energy increases. Two, also the width of the distribution increases. At higher temperatures, I have a much wider distribution. And that is, for example, one of the reasons why in my field, when I do research, I measure stuff about, ions in the gas phase that are energy selected. And one of the ways to energy select, or part of the energy selecting process, is to cool down the molecules a great deal, because at the lower the temperature is, the narrower the distribution. So if you go from 300 kelvins to, let's say, 30, then now we have a much narrower distribution of speeds, and so it will be much more accurate. It will be much more precise, actually, much less of a spread in the internal energies. Okay, but the bottom line is that this distribution tells you what are the likelihoods, what are the probabilities of finding particles with given velocities, and that depends on the temperature. And again, the two effects is higher the temperature, higher average velocity or average kinetic energy, and then also the wider distribution. And again, it is because, just like when you look at a crowd and you just let people go around, or just a bunch of flies in a room, they each travel with a different velocity, but of course there is an average. Now, how does it depend on the speed? How does the speed depend on the mass of the gas? And that's kind of important, right? Because you know that the kinetic energy is just a measure of the temperature, the average kinetic energy. What is the average kinetic energy? It's something like the half times the mass of the particle times the velocity square, right? And that is proportional to temperature. But the same for each gas. And so since this at the given temperature is constant, then what I have is the mass times the velocity square is constant at the given temperature. Therefore, the higher the mass, if this increases, this will have to go down, right, in order to have the same kinetic energy. And so if you look at the x-axis as molecular speeds, the lighter the particle, the higher the velocity. So if you look at oxygen with 32, nitrogen with 28, water with 18, and helium with 4, their average velocities, the molecular speeds, will increase, right? Since this is squared, then it will be proportional to 1 over the molar mass, right? Why square root? Right, because the velocity square is what is inversely proportional to the molar mass. Right, and so now we can use this Maxwell-Boltzmann distribution, and this just says that what is the probability number of particles with different with the particular velocity over the total number of particles. And so we have this formula. This is just a scaling factor, and it will depend on a v squared times e to the minus mv square, and again some over rt with some scaling factors here and there. But the bottom line is that this is giving you that particular distribution, and if you know the mass and if you know the temperature of a particular gas, you can actually calculate the actual numerical distribution, the quantitative distribution of the velocities for that. And if you do that, if you have that function, right, then you look at, let's say, the most probable one. What would be the most probable one? Well, the top, right? So where is the top? So what you would have to do is take the first derivative with respect to velocity. You know how to do that. And when that is 0, that will give you the most probable one. Or you can take the distribution and average it, and that would give you the average velocity. This most probable speed then depends on the temperature, right? The higher the temperature, the higher the most likely speed, and it's also inversely proportional to the square root of the molar mass, right? So the heavier it is, because the kinetic energy is what's proportional to the temperature, the slower it moves, and that factor is, you know, square rooted because it's the kinetic energy, which is v squared, that scales. So there are the averages, right? So the thing is, when you have this distribution, right, you can also look at where will be the average velocity. But that's not always terribly useful. You can do that, you can take that function, you can calculate the average speed, and the average speed is about 13% higher than the most probable speed, okay? And then the reason is that, you know, there's a significant tail at high velocities, right, on the distribution curve, and that will, you know, pull the average higher. But there's a much more useful way of averaging, and why is that? Well, remember that it's actually the kinetic energy that we're talking about, the kinetic energy that is proportional to the temperature. And so if we're averaging not in terms of velocities but velocity squares and then square root it, then what we have is the root mean square velocity. Root, that is a square root of the mean of the squares of the velocities. And so we're averaging the kinetic energies of the particles, and then after the averaging, you take the square root again to get the velocity back. And this will be a different way of averaging, right? It will be a way when we're averaging in terms of kinetic energies, right? And so that would mean square velocity is a little bit between the most probable speed and the average speed. It's 1.085 times the average velocity, and it's a good exercise to do these averages if you happen to be, you know, like physics, or if you're a mechanical engineer or something, and if you like math and that sort of stuff. But anyway, so the importance of this is that since it runs in kinetic energies, right, squares and velocities, the kinetic energy average you can actually obtain from the root mean square velocity. That square times mass times 1/2 gives you the average kinetic energy. Now, what about the limitations of the kinetic theory of gases, right? So we started out with a few assumptions on how a gas behaves like. So one thing was that the volume of a gas molecule is insignificant compared to the volume of a gas, okay? So compared to the available volume for a gas, the particles are very, very, very small. And so we can test this assumption by looking at the mean free path. The mean free path is how far a particle can travel between two collisions, right? What is the average distance that they fly between collisions? And so for let's say air at room temperature or something of that sort is about 70 nanometers, right? So that's actually a kind of a small distance, you know, on our scale. That's roughly 200 times the radius of a small molecule, right? And so since, you know, volume scales with the cube of the linear distances, that means that the volume of the empty space is 1 million times the gas particle volume. So is this a good assumption? Well, when we're talking about, you know, atmospheric pressure, it's actually pretty good. But when we increase the pressure, when we compress the gas into smaller and smaller volumes, then they can get much closer together, and then suddenly that individual volume will start to make a difference. Now, one more thing is that when we talked about the kinetic molecular theory of gases, we just said that, you know, they fly in straight lines, no interaction between the particles, they just collide, but it doesn't matter, they collide with the walls, and that's where the force, the pressure is coming from. Well, this means that the gas molecules neither attract nor repel each other, okay? And that is, you can also say that the attractive forces between the particles is very small compared to the average kinetic energy of the gas molecules. Now, if you, however, decrease the temperature. If you decrease the temperature, that will decrease the kinetic energy. And if you decrease the kinetic energy, that means the particles will travel slower, and then suddenly the forces between them will be more significant. Let me give you an example. So let's say we're both walking on campus and we bump into each other and then do a little chit chat and then keep walking, right? Let's say you're going to a class, I'm going to my lab or something. And then how much chat we can do, how important is that little attractive thing that's going on, depends on how much we're in a hurry. If we're both running, we'll probably spend only a few seconds in close vicinity, and so there will be not a meaningful interaction between us. If we have nothing else to do when you slowly walk, then we have more interaction to do. And that's similar here too. The lower the temperature, the lower the average kinetic energies, and therefore, compared to that, these attractive forces will be more important. Okay, and so when are these attractive or repulsive forces significant? When we have low temperature, right? Because the kinetic energy increases temperature, and so now we have sort of sticky collisions, right? Collisions where the attractive interaction is significant compared to their kinetic energies. And therefore, they will pull these gas molecules together, and that will decrease the pressure that they exert on the walls. Why? Because the other particles are pulling back on them. Now, the other thing is, what about the volume of the gas? If you have extremely high pressure conditions, then you're decreasing the available volume for the gas molecules, and therefore the volume of the gas particle becomes more significant. And then as the pressure increases, this mean free path decreases, right? We are squeezing the molecules closer together, and then the volume of the gas particles becomes significant. And so these are the limitations of the kinetic theory of gases, right? At high pressure, because of the individual volume of the particles. And then at low temperatures, because of the attractive forces, right, between the particles, right? So high pressure and low temperature is when these come most importantly into play. Again, high pressure because the volume of the particles, and low temperatures because now their kinetic energy is smaller compared to the interaction energies. So how can we correct for it? Now that's the beauty of science, right? If you understand the underlying assumptions, the underlying physics in this case of the equation, then you can also correct for it. So let's start with a simpler one, and that will be correcting for the volume. And so what is the available volume for a particle? Well, it's the total volume minus its own volume, right? And so what is its own volume? Is that the volume of a particle times how many particles you have. And so if the volume of an individual particle, right, the volume of a particle, right, times how many particles you have, and that is the number of moles, right? Okay, not one particle, 1 mole of particle, okay, whatever. Okay, and then you simply subtract this from the total volume available for the total volume of the container, then this would represent the available volume for the particles to go around, right? So this is a very simple correction to the PV equals nRT. Now what about the pressure? Well, the pressure that we measure is going to be reduced, right, by this attractive interaction. So the measured pressure plus some sort of a correction factor is what we would have under ideal conditions. And so that would be here, again, some sort of a fudge factor, but then how many interactions we have depends on how many particles we have. What is the total volume for the particles? And since you need 2 particles for the interaction, then it will be N over V for 1 particle. How many particles per volume? And then for the second particle is also N over V. So we have N square over V square times, again, some factor. And so that you put into the pressure expression, then we already done the correction for the available volume, and now we simply have a corrected, a more accurate gas equation, and we call it the van der Waals. Okay, so the van der Waals is a real gas law, and then the A corrects for the attractive forces. That is, the larger the A, the stronger the attractive force is here, right? And then the B corrects for the own volume of the gas molecules. The larger the molecules, the larger B values you have. That's not strictly true. It actually has some quantum mechanical effects too, like how smeared out the particle is, but that's a little bit and I guess that's why this one only lists helium. Oh well, there's helium and argon, and if you listed neon, then you know what I'm talking about. But roughly, let's just look at these. Okay, so helium, you see that the attractive interaction is almost negligible, 0.034. Similarly, if you look at hydrogen, there's not much interaction between two hydrogens. The larger the particle, the more dipole the particle has, the stronger the interaction. So if you look at sulfur dioxide, huge interaction. Water, very large dipole, a lot of interaction. So the A really depends on how strongly these molecules are attracted to each other. And then the B is pretty much the size, right? Kind of like that. So if you look at sulfur dioxide, that's much bigger than let's say just oxygen, right? Without the sulfur in there. The smaller ones are, you know, the atoms here, right? This is argon, this is helium, and then hydrogen anticipated is small, right? Because it's, even though it's two atoms, but it's the smallest of atoms, right? So this is small as well, right? Small. But you can see that sometimes, you know, it's not as simple, because for example, helium for hydrogen fluoride, that actually seems to be bigger than the water, right? Even though, right, the water molecule is actually it has two hydrogens, so overall volume wise it's bigger, but it's the effective volume within which they start to feel each other's effect, right? So that's why it's not as clear cut as that. We can just, you know, take a tape measure and measure the size of the molecule, but you know, this is the size, and this is the relative interactions as they influence their movement in a gas. And so how can we use that? Now we have everything. So if we want to put this together into one calculation, and let's just say I think this is the last calculation. Okay, so let's just do this and then let's get this over with. We have a methane storage tank, right? We have the volume, right? So this is the V, and then instead of giving the number of moles, we have the mass. And in fact, we have the empty mass of the container, and then if we fill it, then this is the mass. So the difference of the two will give me the mass of the methane. So let's do that right away. Just get this out of the way. 62.07 kilograms minus, okay, 55.85 kilograms. So that gives me 62.07 minus 55.85, that is 6,220 grams. Okay, so this is the grams of the methane, but of course I want moles, so 620 grams of methane times 1 mole of methane is 12.011 plus 4 times 1.04, and that is 16.043 grams of methane, and then that will give me the moles, right? So right away I have 387.71 moles of methane. Okay, so that we have. Now what about the temperature? The temperature is 21 Celsius, so that will be 294 plus 0.15 Kelvin. So I have the temperature, I have the volume, I have the moles, okay, and so everything is given to get the pressure. So let's start with the PV equals nRT, and that would give me pressure equals pressure from that, so the pressure is nRT over V. Let's just put everything in, okay, so that would be 387.71 mole times 0.08206 liter atmosphere over mole Kelvin, just so that I will I will get it in atmospheres. And now the temperature is 294.15 kelvins, and then I have the volume as 49.0 liters. Now what's the pressure? So 387 times 0.08206 times the temperature 294.15 divided by 49 liters, and that would be 190.99, so 191 atmospheres. Now how many sig figs do I have? This is 3 sig figs, right, because the last significant figure is in the ones. Then here it's a subtraction, so this was the last significant figure, which happened to be this one here. So I have 3 sig figs on that one. I had 3 sig figs there, so it seems like I had 3 sig figs overall, so it's 191 atmospheres. Now let's see if that is roughly correct. So I packed in 300 moles. Okay, so 300 moles would be 300 times 25 liters. Or let's say 400, it's close to 400 times, right? But I only have 50 liters, which would be, you know, only twice the volume, but 400 times the moles. So I anticipate the pressure approximately 200 atmospheres and 191 atmospheres. Roughly correct. By the way, the temperature is close to room temperature. So indeed, this is approximately what we're expecting. But how about, I kind of feel that at 191 atmospheres, 200 times atmospheric pressure, there's something sticking, right? The real gas law should give us a better value. So how would we do that? So the pressure times the A times n square over v square times, and now the total volume is at 49.0 liters, but we're now subtracting b times n, right, the correction for the volume, and that gives me the nRT. So the nRT part is the same. Okay, now this is simply calculated from the volume and the B factor and the number of moles. So the nRT I already have up here, so I can just use that, okay, put it in there, okay, and divide with this would be a 49.0 liters minus, and then what is the I was talking methane, right? Methane is 0.4278, right? So and it's in liters per mole, right? So that would be 387.7 moles times 0.0, and I already forgot, 4278 liters per mole, right? Mole cancels out the mole, so we're indeed doing a liter conversion. So are you interested what that is? So 49 liters minus the moles times 0.0478, that would be only 30.47 liters. So this is a significant correction, right? Instead of the 49 liters with 0 particle volume, at this 191 atmospheres, now it reduces by well over a third of the available volume. More than a third of the volume is occupied by the molecules themselves. So that is some crazy large value. And so now with that and the nRT, I can just calculate the pressure and then subtract the correction. So the uncorrected pressure would be, now where do I have that? Okay, I think I have the mess it up. Okay, so I have the moles, okay, times 0.08206 times 294.15 divided by this new corrected volume, and that would give me 307.17 atmospheres, right? So it's much higher pressure, in fact, than what we're expecting. But then we would have to subtract the correction for the now, does it sound reasonable? Why is it a higher pressure? Well, the higher pressure is because now the molecules have a lower volume available, right? When you subtract their own volume. And then I have to subtract that A, which is 2.253, not writing out the units, it's boring, times the N square over V square, and that V square is at 49.0 liters, and that squared. So again, that's some crazy numbers here. And then please do this calculation yourself too. Don't just trust my numbers. So I'm squaring the N over V and now multiplying it 253, and then the correction I have is 141.06 atmospheres. And if I subtract that from the calculated 307, then I get the pressure is 166 atmospheres. Now, this is kind of a crazy result. Why is that? Well, first of all, we have to realize that there are two opposite effects here. One effect is the available volume, and the available volume decreases, thereby increasing the pressure to some crazy anticipated value. But then we would have to subtract the effect of the interaction between molecules, the attractive forces, and that attractive force actually decreases by more. And so the overall force that we're feeling, the overall pressure that we're feeling in this gas is only 166 atmospheres because of the two opposite effects. Now, I hope I haven't made some horrible mistake, but if I haven't, then this is a very good test of, how to employ the van der Waals equation. And with that, we're going to simple things. Just a few, since many of you are engineers, just a few remarks on how we can measure pressures, because this is of course very important. The one is the what we call the capacitance manometer, or we just call it barometron actually, because that's a trademark, and then everybody calls it barometron. Trust me. And so what we have is a diaphragm which is flexible, and so the flexions in this diaphragm depend on the pressure, and that changes the capacitance. And then with the electronics, you can measure the capacitance, and this measures absolute pressures. It doesn't depend on what kind of a gas this is, right? Because all you're doing is just hitting this wall here. And so the capacitance manometer works the same as nitrogen, as oxygen, as other gases or noble gases. And it used to measure small pressures, 0.001 torrs. So a millitorr, that's kind of pushing it, but a good barometron can probably handle it to approximately atmospheric pressures or slightly above. Okay. Now that was the barometron. Now a thermocouple gauge, what happens is that it measures the pressure by the cooling effect of the colliding gas molecules, and the more gas molecules you have, depending on the gas molecule, of course, the more heat will be transferred away from the heated filament, and then lower the temperature will be. So you put a certain amount of power on the filament, and then temperature will be determined partly by how much gas is there to take that heat away. And then this needs to be calibrated for a particular gas, because different gases transfer heat differently, and it's typically used for lower pressures than a barometron. It's typically measured for used for measuring vacuums, right? The pressure in low vacuums. Now, high vacuum, that is much lower temperature, can be measured by an ionization gauge. An ionization gauge is actually pretty funky. So what we have here is first a filament. The filament is not for the temperature, but to emit electrons. So at a hot filament, the electrons are flying off from this wire. And then those electrons get caught in this cylindrical grid. So you put they put a current, actually not voltage, you put a current on this. It's actually a wire. It's like it looks like this, and I'll show you it on the next page. And so what happens is that these electrons are caught in this grid, and when they hit a gas molecule that is coming in from here, then they ionize it, and then the ionized particles can get collected in the middle on this fine wire, and that fine wire, then if it catches these ions that carry a charge, then you have a current, and then you amplify that current, and then the more molecules you have, the better ionizable they are, the higher current you'll measure. And so essentially the number of ions, the number of charges collected will be proportional to the pressure, but of course this needs to be calibrated big time, because ionization energies, different gases behave differently, and you can measure down to 10 to negative 11 torrs, which would be 10 to negative 14 atmospheres roughly, or something of that sort. So very low pressure. So this is what we use to measure high vacuum. So for example, on my instruments upstairs in my lab, we have both the previous, actually all three. We use barotrons for mixing gases, but for low vacuum pressures we use these thermocouple gauges. Then for high pressures, in our case it's down to 10 to the negative 7 torrs or millibars, we use these ionization gauges, and this is indeed how they look like. So this is an ionization gauge here. You can see these the coil here, and then in the middle this is connected. So actually you're putting the wire on this little thing here, and then this is where these connectors are, where you're connecting to both the current for the coil and for the voltage for the filament. Then this is the barotron, so that is to use to measure absolute pressures, and then this will be a thermocouple gauge here. Okay, so with that, let's stop here. That is the end of chapter 5, the gases chapter, and then this is kind of a chapter where there's lots of good calculations to be done, even simple ones, like when I'm changing the temperature, how does the volume change, or pressure and volume, pressure and temperature, or the full calculation with the ideal gas law. Then also even partial pressures, and with the Dalton's law of partial pressures, there's a lot of calculation. And of course the PV equals nRT can also be used to do stoichiometry calculations. So there's a bunch of gas stoichiometry that we can do in this chapter. And if we want to go really, really tough, then at the end we can even use the real gas law, like van der Waals, to calculate a more accurate pressure under weird conditions, let's say very high pressures when you're really compressing the gas. So my recommendation is, when you're done with this chapter and you think you understand the theory, understand the basics, then just do a bunch of calculations, and then get really friendly with your calculator, because it's easy to make little mistakes. And then one more thing, sig figs. Always mind the sig figs in these calculations, especially know that when converting from Celsius to Kelvins, then it's an addition, right? And then an addition has a different sig fig rule, right? So for example, if I say 11 Celsius, that's actually 3 sig figs in the ideal gas law calculation. Okay, so thank you so much for watching. This was chapter 5 in CHEM24.